Hello, this is Dr. Anna, and I am your physical geology professor. And today we're going to talk about earthquakes. Um, so here is the deformation of earthquake. It is a trembling or shaking of the ground, and it is caused by the sudden release of energy, which is normally stored in the rocks beneath the Earth's surface. The first thing we have to know is the elastic rebound theory, which was done by a seismologist. His name is Reed. He set it up as a three-step process. First, the rocks are standing with stress acting on them, and then the stress causes strain in the rock, and the strain builds up for a long period of time until the strain gets beyond the rock's breaking point. As soon as it happens, the rock breaks suddenly and it will release energy, and the rock is always moving along a fault. Every single earthquake is always happening because there is a fault happening. Um, the faults can move horizontally or vertically, um, and the energy will be released in form of seismic waves. And this shows you just the pictures for the elastic rebound theory. This is the rock just relaxed, that's the stressed one, and this is when it's breaking. And this just shows you the earthquake itself. So when the earthquake happens, you're going to have a fault line forming. At the point where the earthquake exactly starts is what we call the focus. From the focus, the seismic waves are moving along a sphere. So you have to imagine it's a three-dimensional. It moves along a sphere, and as soon as it reaches the surface, at the point which the seismic wave reaches the surface is exactly above the focus, and we call the epicenter. From the epicenter, the waves are spreading along circles, so it becomes two-dimensional, just like when you throw a rock in the water. It's exactly the same way. Okay, the seismic waves can be divided into two major groups. One is the body wave and the other one is the surface wave. So now we're going to talk about body waves. The body waves are traveling through the earth interior, and they're spreading from the focus along a sphere in every direction, just like the sound waves. The body waves do not cause any damage to humans because it's just traveling through the earth. As soon as it reaches the surface, we call them surface waves. So those are the ones which causing us the problems. We have two kinds of body waves. The first one is the so-called P wave. P stands for primary, so P or primary wave. This is a compressional wave. It will move like this. It goes out the screen anyway. So the P wave moves like this. It's also called longitudinal, and in these waves, the wave will travel parallel to the direction of the propagation. It is a very, very fast wave. That's why we call it primary, and it travels between 4 to 7 kilometers per second. Because it is fast, this usually is the first wave to arrive at the seismic station after an earthquake. So this just shows you the way it travels. The next type of wave is the so-called S wave or secondary wave. This one is slower, and the way it travels is that it goes up and down. But this is the propagation. The secondary wave moves like this. So it goes 90-degree perpendicular to the propagation of your wave. The speed of this, it's, as I said, it's slower. It goes 2 to 5. But it's really interesting that I hope you remember the first one, the primary wave, went 4 to 7. This guy is going 2 to 5. So you can see the range is exactly the same in both cases. What do you think? Why do we have this difference? Yes, the different density rocks will cause the wave speed up or slow down. The more dense the rock, the faster the wave goes. The less dense the rock, the slower the wave goes. So it depends on the density of the rocks. Okay, as you can see, this here is the P wave, primary, and this here is the S wave, the secondary. Now, both of these body waves pass through solid rocks really easily and well. However, the S wave will not go through liquid. This is very important. The S wave will not go through liquid. They usually are faster in dense rock and slower in unconsolidated sediments. The second type of waves are the surface waves. Remember, the surface waves are starting when the first spherical wave propagation reaches the surface at the epicenter, and from the epicenter, the waves are making circles going out from the epicenter, just like you drop a rock on the water. So the surface waves are strictly traveling on the surface. They usually much slower than the body waves, and they are the ones causing all the damage to humans because the ground movement is being caused by them, and they are slower, so they will take slower to pass through the material. And probably you do remember these pictures. This is just the all the earthquake waves. The P waves are going through liquid, the S waves will not go through liquid, and the surface waves are always on the top of the surface. So the way we locate and measuring earthquakes is our next topic. First, we talk about the seismograph. The seismograph is the equipment with which we're actually going to record earthquakes. The seismograph have usually a stable and a moving part. Normally, they would put the seismograph somewhere where it's far away from all the human noises like trains or big trucks or stuff like that. So you want to put it somewhere in the woods where there is no any kind of disturbance, and you want to put it like deep enough so it will pick up all the earthquakes, but it won't pick up any surface noise. Because the way the seismograph is set, that it has to set at the sensitivity, which means that it records even the smallest earthquakes, but they don't record the surface noise like people's noise, trucks, trains, as I just told you. So when the sensitivity is set right, then it should be able to record even an earthquake one, like a very low intensity earthquake. So the moving part of the seismograph is what records the so-called seismogram, and this here is the seismogram. The seismogram used to be on a drum next to the seismographs, hooked up with the unmobile part, and the writing mobile part is actually making the seismogram. The seismogram, the main thing of the seismogram, there is time. So therefore, when a P wave arrives to the seismic station, it will make a big mark right there. And then you will see the time of the S and the time of the surface wave. So this is just the way it goes. Today, we don't have paper and drum. We actually have digital seismic recording. Like at Virginia Western, we have a seismograph, which is digital. And the seismograph is in the ground in a concrete tube. And inside that, the seismograph itself has a digitizer, and it gets energy from a solar panel, which is connected to batteries, and the batteries store the energy, and that is supplying electricity to the digitizer. The digitizer records an earthquake, and through an antenna, actually, it goes into our business science building where it gets to the computer. So basically, anytime there's an earthquake, you can see the record basically right away. Now, what is really interesting, actually, shows you like a 24-hour record of a seismograph. And if there is an earthquake, the first which comes in is the P wave. The second one is the S wave, and then the surface waves. Now, what is important is, which helps us to tell where the earthquake happened, so to locate that earthquake, the important thing is to see the delay time between the P and the S waves. Because P wave travels 4 to 7, S wave travels 2 to 5. So the distance in that time, arrival time, is going to be related to the distance from the seismograph to the epicenter of the earthquake. So this is a very important measurement we'll have to do on the seismogram. This just shows you a couple of earthquakes. Like this one happened really, really far away. So the next thing is that we have a network of seismographs. It's throughout the earth. So if there is an earthquake or nuclear bomb explosion, minutes after that, the seismographs are going to record it. If you have a very large earthquake, it will be recorded on every single seismograph on Earth. If you have smaller ones, they only are going to be recorded in local little seismographs. Every single seismic station will have a so-called travel time curve. The travel time curve basically translates the time into distance, because that's what we need to know. We have the difference in the arrival time, and we have to tell how far it was. So we travel the time into distance. And the way we do it, that on this travel time curve, this shows you the time, and this shows you the distance. And you can actually plot on this the slower P waves and the faster S waves. And what you do is when there is an earthquake, you're going to actually fit the seismogram on this curve. And wherever the time difference between the P and the S waves fit on the curve will tell you the distance of the epicenter from the seismograph, from the seismic station. Okay, so you always try to fit the seismogram on this curve, and wherever the P and the S peak reaches the two curve at the same time is where you go down and get the distance on your from the seismic station to the epicenter. Now, when you get that distance, all you can do is just plot it. Like if this is your seismic station, let's say Virginia Western, and we see that there was an earthquake, which is about 75 kilometers away, or miles, it don't matter. So we know that the radius is 75 miles. I just put M. And that's all we can do. We know that there was an earthquake in a circle which has a 75 miles radius. That's all. So one seismic station will not locate the epicenter of any earthquake. We need at least 3 seismic stations. If we have 2, see, that's the other one. Let's say it was in Washington, D.C., and it was like 250 kilometers. See, this will actually cross our original circle 2 places. So 2 seismic stations will not give us the epicenter. You need at least 3. If we have a third one, then we can tell that this is the epicenter of the earthquake. So this is very important. This is the triangulation, and this is what we use every single time. Not we, but seismologists use every single time to calculate the location of the epicenter every single time, just like here. That's the epicenter right there. I'm going to finish this segment right here, and I'm going to continue on the next one, okay? I'll see you in there.